This is the fourth lecture of rotational mechanics. Okay. See, by now your JEE mains is already over. Okay. The paper has been, some shift. It has been easy. Some shift. It has been difficult. Okay. So if you have scored decent marks around 160 to 180, okay, or above that, just apply for JEE Advanced. Okay. Just enroll for yourself. Doesn't matter you will get or not. Okay. Your registration will start on 7th April, or your registration has been started on 7th April. Okay. 7th April and will continue to 2nd May. Okay. JEE Advanced registration. Advanced registration. Just go to the website and register yourself. Okay. Your examination will be on 18th May. That is a Sunday. Exam or JEE. So you have around 1 month and 10 days. 10, 20, 10 to 15 days. Okay, for your examination. So now what to do? See, whatever your preparation was till JEE mains, okay, continue with that. That means suppose you keep on revising your syllabus every week or every kind of test series, that kind of every 7 weeks, or not every 7 weeks, every 7 days you keep giving test series, full syllabus test series, you revised all the formulas. So keep doing that. Okay, that should not be skipped. That means complete your revisions for JEE mains every 7 days. Okay, and apart from that, see, if you're attempting new type of question, attempt subjective questions or difficult subjective questions. Difficult subjective questions. Subjective questions. Okay. It would be better if you focus more on the numerical type, but go for proof also. Okay, proofs also. Because even if the proof doesn't come, the concept will be there. Okay. The concept will be twisted in the question and ask for the numerical value. So focus more on the numerical subjective questions, but go for proof also. Okay, do not skip those proof. Yeah, from where to do those subjective questions? See, most of you have started with HCV. Okay, in the back of HCV there are very good subjective questions. Okay, so in questions of HCV are very good. So complete the HCV questions. Okay, whatever you haven't solved, and after that go for irodov. Enough. This much is enough for your JEE Advanced preparation. Okay, see, the questions that are coming in JEE Advanced are from various sources. They use recent holiday, they use irodov. Okay, some conceptual questions are there, some new questions are there. Questions have come from MIT past papers. Okay, Massachusetts Institute of Technology. Questions have come from Olympiads. Okay, so you cannot cover the entire base of question bank. You cannot cover entirety because you have to deal with three subjects: physics, chemistry, and maths. And for all those three subjects, if you try to cover everything, nothing will happen. Okay, so for physics, difficult subjective questions, just go for HCV and irodov. Okay, and do not forget to revise your JEE mains preparation every 7 days. Okay, you just keep doing this and you go to the exam and you say, sir, this did not come, or I haven't completed something kind of thing. So do not forget or revise JEE mains whole syllabus, whole syllabus every 7 days, every 7 days. That means you get around 4 kind of revision. Okay, okay. Do not skip this part. Okay, that means you just have to recall the formula. No, you do not have to learn all those formula again. You just have to recall the formula of what you have studied, isn't it? And having revised some portion, just go for the difficult questions, because although this is important, this is not the main crux. This outer is the main crux of your revision. Okay, this will keep you stable, or this will give you stability. Okay, and this will give you the edge. Edge means how much more can you perform better than the rest. So if you focus on edge before giving you stability, will perform very bad. Okay, so this thing that I've said, revise your JEE mains whole syllabus every 7 days. That is the main crux of your preparation, and this is nothing but improvement. Okay, or improvement of marks. Because even if you start now, you cannot complete entirety of it. Okay, a kid that has started 2 years earlier of solving irodov, we cannot do it in 1 month, or you cannot do it in 2 months also. You require significant amount of time. So do not forget this part. This will give you the main stability of JEE Advanced. Okay. So having said this much, let's move forward to our question. Question number 1.250. See, this question is very simple. Okay, I'll just translate this question in linear mechanics. Okay, so I'll give you a problem of linear mechanics. Whatever you do in that solution, or whatever your intuition is for that solution, the same kind of solution will be applicable out there. Okay, so let me just translate the question in linear mechanics. Suppose a block is there. Okay, it is moving with initial velocity v naught. Okay, the block is moving with initial velocity v naught. Air friction or drag forces. Okay, drag forces are acting in opposite direction. Drag forces. What is drag? Drag is nothing but air friction forces. And that drag forces is given by the formula. Drag force is given by formula some constant into the velocity or into instantaneous velocity of this block at that moment of time. That means when this velocity is v naught, the drag forces acting would be k into v naught. Okay, when after the drag forces act, what will happen? The velocity will reduce. So after a certain time, it will be something lesser than v naught. Let's say 5 meter per second. So when the velocity is 5 meter per second, the drag forces will be k into 5. Okay, then again some amount of velocity will reduce. So you understand what is happening out here. The body is projected with initial velocity v naught, and drag forces is acting in opposite direction. However, that drag forces is dependent upon velocity. That means as the velocity reduces, the drag forces also reduces. We have to find out the average velocity. Find average velocity for the total time traveled or for the total distance traveled. Okay. So what is the total distance traveled? Till its velocity become zero, isn't it? Total distance. This block will only move till its velocity becomes zero. No? After its velocity becomes zero, the drag forces no longer acts on the body, isn't it? And what is the formula for average velocity? Total displacement by total time. Total displacement by total time, isn't it? And how do I find out total displacement? Force is equals to mass into acceleration, isn't it? This is the main formula I use. What is force out here? Kv. Mass, acceleration can be written as d or v dv by dx. V dv by dx. So from this equation, I'll get the total displacement because I know the initial and final velocity. No, initial velocity is v naught, final velocity is 0. So from this equation, I'll get the total displacement. I can also write the same equation. F is equals to ma. What is the force? K into v is equals to mass into acceleration. Acceleration can also be written as dv by dt. dv by dt. This would be our equation number 2. And from equation number 2, I'll get the total time. Now when I divide the total displacement by total time, I'll get the average velocity. The same thing is happening out here in this question. A flywheel. Okay. Now you might ask, sir, what is flywheel? Flywheel is nothing but a wheel with mass m. Okay. Sir, where it is used? Have you seen that sugarcane juice machine? The person rotates and a big wheel is at the side of the sugarcane. No, that big wheel is nothing but a flywheel. The job of that flywheel is to store mechanical energy and give it when it is needed. Okay, it acts similarly to a capacitor in electricity. Okay, that means, see, what the flywheel does is stabilizes my input. So when no sugarcane is there, I keep giving it effort. So all the mechanical energy that I'm giving my effort is stored in rotating the wheel, or stored as mechanical energy in rotating the wheel. And when I input my sugarcane into this crusher, what happens is I do not need to apply more strength. The mechanical energy that is stored in the flywheel will provide me with the additional energy that is required to push the sugarcane. Okay, so for now, just remember a flywheel is nothing but a ring with mass m. Okay, so ring with mass m and moment of inertia I. Okay, and this is rotating with angular velocity omega naught. Okay, a torque is acting in the opposite direction. A torque is acting in the opposite direction, which is directly proportional to the instantaneous angular velocity. Okay, a torque is acting in the opposite direction, which is equals to instantaneous angular velocity. That means as the velocity decreases, the torque will also decrease. Okay, so we know that whenever proportionality sign is removed or replaced with equals to sign, it becomes some constant into this one. Okay, so whenever proportionality sign is removed, a constant is introduced. So torque is equals to, let's say, that constant into omega. We need to find out the average angular velocity till it stops. So similar kind of approach will follow out here. Okay, torque is equals to I alpha. What is the value of torque? K into omega. Value of torque is given as K into omega is equals to I into angular acceleration can be written as omega d omega by d theta. But d theta is the total angular displacement, isn't it? So this is the equation 1. Similarly, the second equation, K omega or total torque is equals to I into angular acceleration. For angular acceleration can be given as d omega by dt. Okay, so from this equation you get the total angular displacement. From this equation you get the total time. And when you divide total angular displacement by total time, we get the average angular velocity. Okay, so let's solve for 1. K omega is equals to I into omega d omega by theta. omega d omega by d theta. And out here, one more thing that I haven't done, one more thing that I have done wrong out here. Initial angular velocity daccelerates due to forces whose moment relative to axis proportional is square root of angular velocity. Okay, that means out here, force is not directly proportional to velocity. Force is directly proportional to square root of velocity. Force is directly proportional to, or torque is directly proportional to square root of angular velocity. So this is the mistake that I have done out here. Okay, reading the question. So torque out here is directly proportional to square root of angular velocity. So out here torque is directly proportional to square root of angular velocity. Torque is directly proportional to square root of angular velocity. Okay, out here root, out here root. The mistake that was done out here is, see the question properly. Force whose movement relative to the axis is proportional to the square root of its angular velocity. It is not directly proportional to the angular velocity. Square root of angular velocity. This statement was my mistake. Okay, this square root I haven't seen in the question. Okay, so replace that one. Instead of V, right? Track force is directly proportional to K into root. Torque is equals to K into root omega. Okay, so we follow the same approach as before. Okay, K under root of omega, or how do I do this? This omega will come down out here, or K by under root of omega is equals to I d omega by d theta, or K by I into d theta is equals to under root of omega d omega. Now when I integrated both the terms, this under root of omega can be written as omega to the power 1 by 2. I simply solve the problem out here. See, I have brought this omega down out here. Now omega can be written as under root of omega into under root of omega. So one of the under root omega will get cancelled, isn't it? This I will come down out here. And if I send this d theta to the left hand side and under root of omega to the right hand side, I'll get this equation. And under root of omega can be written as omega to the power 1 by 2. Now for the limits, the initial angular displacement is 0, the final angular displacement is theta. That's it, or theta naught. The initial angular velocity is omega naught, final angular velocity is 0. Because when the body stops, final angular velocity is 0. Is equals to theta naught. What is omega to the power 1 by 2 d theta naught? Omega to the power 1 by 2 plus 1 divided by 1 by 2 plus 1. The upper limits and lower limits are omega naught and 0, isn't it? So K by I theta naught is equals to omega to the power 3 by 2, half plus 1 is nothing but 3 by 2 divided by 3 by 2. Okay, from omega naught to 0. So K by I theta naught is equals to 2 by 3. Okay, 0 minus omega naught to the power 3 by 2. Or K by I. Let me do this equation properly. K by I theta naught is equals to minus 2 by 3 omega naught to the power K by 2. Okay. Okay. There's certain homework for yourself. You have to figure out why this minus is coming out here. Okay. What is the significance of this minus? I'll give you the hint at the end of the question. Okay. For now, just focus on the solution. Equation number 2. What is the equation number 2? K into under root omega is equals to R d omega by dt. K into root omega is equals to R d omega by dt. Okay. Or same type of problem, K by I into dt is equals to d omega by under root of omega. Okay. Or K by I, let's integrate it from 0 to time t, from omega naught to 0. K by I t is equals to, what is the integral of d omega by omega? It is nothing but omega to the power minus 1 by 2 plus 1 divided by minus 1 by 2 plus 1. Lower limit is omega naught, upper limit is 0. Or K by I into t is equals to omega to the power 1 by 2 divided by 1 by 2. The lower limit is omega naught, upper limit is 0. Or K by I into t is equals to 2 omega naught, or 0 minus omega naught to the power 1 by 2. Okay. Or K by I t is equals to 2 into, or minus, okay, minus 2 into omega naught to the power 1 by 2. Okay. So from first equation, I need the value of theta, total displacement. From second equation, I need the total time. So average angular velocity. Average angular velocity. If you see this symbol, okay, this is nothing but average angular velocity. Average velocity is nothing but v under root. So not v under root, v with an dash. Okay. So from the first equation, what is total displacement? Total displacement is nothing but I by k into minus 2 by 3 omega naught to the power 3 by 2, isn't it? So I by k into 2 by 3 minus is taken out here, omega naught into 3 by 2. Okay. What is total time? Total time is nothing but I by k, or minus I by k 2 omega naught to the power 1 by 2. So minus I by k omega naught or 2 omega naught, sorry, 2 omega naught to the power 1 by 2. Okay, so I by k and I by k are getting cancelled, 2 and 2 will get cancelled. So average angular velocity is nothing but omega naught to the power 3 by 2 minus 1 by 2 divided by 3. These 3 is coming out here. This 3 is coming down out here. So 3 by 2 minus 1 by 2 is nothing but 2 by 2, and 2 by 2 is nothing but omega naught to the power 1. So average angular velocity is nothing but omega naught by 3. So this is your question. Okay. Now the follow-up part. Why this minus was coming out here? This minus is nothing but the result of torque or angular acceleration due to this torque is nothing but opposite to the direction of angular velocity. See, if I use my right hand, what is the direction of angular velocity? This one. But angular acceleration due to torque is acting in this direction. So if this direction is positive, this direction will be negative. So this minus out here, this minus out here, and this minus out here is nothing but the result of torque is acting to the opposite to the direction of angular velocity. Okay. Now in this question, okay, there is a cylinder, a cylindrical pulley. Okay, mass of this cylindrical pulley is nothing but n. Okay. Now there is another chain. Okay, this chain, the entire mass of this chain is, okay, small m, this small m outer, and this chain is wrapped around this cylindrical pulley. That means this much part is hanging, and the remaining part of the chain is wrapped around this pulley. Okay, now x part of the chain is hanging out here. The question is asking, as soon as I leave it, someone is holding this chain. Okay, someone is stopping this pulley or putting a finger out here and stopping this pulley. Okay, the question is asking, as soon as someone leaves the finger, okay, and the chain starts rolling, what is the angular acceleration of this pulley? So as soon as the chain starts coming down, what is the angular acceleration of this pulley? Okay, so whenever such diagrams are there, divide the diagram into equations, linear equations and rotational equations, and find the relation between them both. Okay, so out here, if the entire mass of the chain is small m, if the mass of the entire chain is small m, what is the mass of x part of the chain? See my question once again. If the mass of the entire length of chain is small m, what is the mass of x amount of chain? See, can I say linear density or linear chain density is nothing but mass of the entire chain, small m, see, divided by length of the entire chain is equals to the linear density of the entire chain is equals to linear density of this much chain, isn't it? Because the chain is made up of same material, of same thickness, isn't it? Okay, so this much chain density or the density of chain for this much section is equals to density of chain for the entire length of chain, isn't it? So is equals to mass of this much part of the chain. Let's say mass of this much part of the chain is nothing but mh, or mass of hanging part of the chain. Okay, is equals to mass of hanging part of the chain divided by length of hanging part, isn't it? Divided by this much length. Okay, so if I take these two equations, mass of hanging part of the chain is equals to total mass of the chain divided by total length of the chain into length of the chain that is hanging out here. Okay, so mass of hanging part of the chain is nothing but this much. Now my problem becomes very simple. A pulley is there, okay, and a hanging mass is there. Okay, now this hanging mass, okay, this hanging mass, can I substitute it for a block of mass mh? Okay, and this thread out here has no tension. Okay, this hanging mass is substituted by a block which is tied to a string of this pulley. Okay, this much is done. Okay, and there is one more mass that I have not taken out here. See, if this much part of the mass is hanging, the rest of the mass is wrapped around, or the rest of the mass of the chain is wrapped around this cylinder, no? So this rest of the mass of the chain is wrapped around the cylinder. So this much is nothing but rest of the mass of the chain. Okay, understood? And what is remaining mass of the chain? Remaining mass of the chain is nothing but m by l into remaining length. What is the remaining length that is wrapped around the cylinder? Entire length minus x, isn't it? Entire length minus x. Okay, mass of this pulley is nothing but capital M. It is given in the question. Mass of the pulley is capital M. Radius of the pulley is nothing but r. Okay, so this is my problem. Now if I draw a free body diagram, okay, image is hanging out there, gravity force, tension force, okay, and it is coming down with acceleration a. It is coming down with acceleration a. Okay, now if you see at the point at the edge of the disc or edge of the cylinder, see, if this mass is moving down with acceleration a, this point, the point at the edge, would also move down with acceleration a, isn't it? This point would also have an acceleration a, okay, and this pulley would rotate with angular acceleration alpha. The relation between alpha and a is nothing but a is equals to alpha into r, but r is the radius of the pulley, isn't it? So a is equals to alpha r. This is the main crux of the question that you have to understand. Okay, if this block or if this mass or if this chain is moving down with an linear acceleration a, this point or the point at the edge of the disk, this point, okay, this point, the point at the edge of the disk will also move down with acceleration a. So if this is moving down with acceleration a, the relation between alpha and a is nothing but a is equals to alpha into r. So this is the main crux of the question. After that, let's draw the equation, or let's write the equation. T minus mhg, T, or not T minus mhg, mhg minus T is equals to mh, but mh is nothing but mass of the hanging part. The second equation will come from the pulley itself. So this is the pulley, mass m, okay, this is the hanging part, not hanging part, this is the part that is rotated around the pulley. The mass is nothing but m by l into l minus x, okay, and there is a tension force T down out here. Why is there a tension force T down out here? See, if this block experience a tension force due to string T or due to this string T, out here also there will be equal and opposite T, no? So this T or this T is causing a torque in this disk, which is causing the disk to rotate with angular acceleration alpha. Okay, so the torque, this torque due to tension force is causing this angular acceleration alpha. This much is understood. Okay, now let's write the equation. Total torque is equals to moment of inertia into angular acceleration. What is the total torque? T into R. Total torque is nothing but T into R. Okay, is equals to moment of inertia, total moment of inertia. Total moment of inertia of this disk is nothing but moment of inertia due to the cylinder. Is nothing but a mass square by 2 plus moment of inertia due to this chain. The moment of inertia due to this chain is nothing but mass of this chain, which is nothing but m by l into l minus x into distance at which this chain is kept, that means r square. This mass into r square. This is nothing but moment of inertia into alpha. So total torque is equal to total moment of inertia into alpha. Now let's just simplify this part. Okay, let's take r square, or let's cancel this r in this square. So T is equals to m r by 2 plus m by l minus x, and I'm taking r common. Okay, r. Let's not take r common right now. Let's first simplify alpha. Alpha is equals to a by r. From this equation, I can get alpha is equals to a by r. So this alpha out here is reduced to a by r. Now this r and this r would get cancelled. Okay, so let's cancel this one. So I get my equation T is equals to m by 2 plus m by l into l minus x into a. This is my second equation. Now solving this first equation and second equation, I'll get the value of a. Okay. In the question, however, the value of angular acceleration is asked. Okay. So if I found out the value of a by solving these two equations, can I use this relation to find out the value of alpha? Sure, I can, isn't it? So first, let me solve this two equation. Okay. Equation number 1. What is equation number 1? Mag minus t is equals to Maj. Mag minus t is equals to Maj. What is the value of Maj, or mass of the hanging part? Mass of the hanging part is nothing but m by l into x. M by l into xg minus t is equals to m by l into x a. This is my equation number 1. What is my equation number 2? M by 2, or t is equals to m by 2 plus m by l plus this much, or value of tension force is nothing but this value. So if I substitute the value of t out here, I'll get my equation. So m by l into xg minus t. What is the value of t? The value of t is nothing but m by 2 plus m by l into l minus x into a. Value of t is nothing but this parameter. So value of t is nothing but m by 2 plus m by l into l minus x into capital A is equals to m by l x into a, is equals to m by l x into a. Okay. Now what are the things that we can cancel out here? Let's see. Okay. Let's first simplify. Okay. Let me take the a term common. That means m by l x g, and this entire term will be sent to the right hand side. So m by l x a. I'll just do this quickly. Okay. Plus m by 2 plus m by l into l minus x. Okay. Into a. Let me take a common. This a is taken as common. Or m by l x into g is equals to m by l x plus m by 2 plus m by L into L minus x into L. Okay. Now if I add this term and this term, m by L plus m by L, sorry, m by L x, m by L into x plus m by L into L minus x. If I add these two terms, I'll get m by L x plus m by L into L minus x. I'll get something by m by L. See, m by L x plus m L by L plus, sorry, minus m x by L. Okay. So I'll get this, and out here I'll get m. Okay. So if you add these two values, this value and this value, I'll get m. Okay. So m L by x into g is nothing but m plus m by 2 into a. Okay. Or a is equals to m L x g by m plus m by 2. Okay. This is the value of linear acceleration. The question, however, asks us the value of angular acceleration. Alpha is equals to a by r. So if I divide the entire thing, okay, a by r is equals to alpha. What I did out here, see, I just applied the relation alpha is equals to a by r. Okay, that means the value of a is this much. If you divide the entire term by r, you get the value of alpha. Do it like this: alpha is equals to a by r. Okay, alpha is equals to, what is the value of a? M by lx g divided by m plus m by 2. M by L x g divided by m plus m by 2. Okay, this is the value of a. And what do I need to do to the value of a? I need to divide it by r, isn't it? So divided by r. So this is my value of alpha, or this is my value of angular acceleration. Okay, so there goes this question. Now we'll briefly talk about rolling motion. Okay, so let's start with rolling motion. Now, before we start with rolling motion, the first thing you need to understand is what is rolling. Okay, it's a combination of sliding and rotating motion. Okay, sliding means it's a combination of linear plus rotational motion. Okay, so you have understood few basics of rolling motion in your classes. That rolling motion is a combination of linear motion plus rotational motion. Then you have for pure rolling, unpure rolling, rolling plus sliding. These somewhat you have covered in class. Okay, I'll cover them again. Okay, and I'll give you the in depth of what was happening out there. Okay, so let's start. Rolling motion is nothing but a combination of rotating motion plus linear motion is equals to rolling motion. Okay, rolling motion. Okay. Now, where does a body roll? The body rolls on a surface. So suppose a surface is there. Okay. Okay. Now a wheel is there. Okay. A wheel is there. It is rolling. Rolling means the wheel is rolling in this direction. Okay. And this rolling motion is a combination of rotational motion plus linear motion. That is nothing but the rolling motion. Now this rolling motion, the rolling motion that I gave out here, okay, can be classified into two categories. The first one is pure rolling, and the second classification is impure rolling, impure rolling. Now, basically in physics, we don't say impure rolling. We use another term for impure rolling, that is rolling plus sliding, or sliding plus rolling. Okay, so instead of using impure rolling, we'll use sliding plus rolling. Okay, sliding plus rolling. Okay. Now, what's the difference between pure rolling and impure rolling? Okay, how do we calculate those, or what kind of numericals comes out here? We'll discuss all that, but there are few terminologies that you have to, pay attention to out here. The first terminology that will come again and again out here is nothing but instantaneous axis of rotation. Okay, instantaneous axis of rotation. Axis of rotation. Now, if you have understood this terminology, okay, every concept of rolling will be very easy. And this terminology is mostly given or mostly taught in the schools in the wrong way kind of thing. Wrong way kind of thing is instantaneous axis of rotation. They have mostly said it's a point of contact. That means at this point. It's not that. The definition of instantaneous axis of rotation is nothing but Suppose a ball is rolling on a surface. Okay. So after a certain while, the ball will be out here. After a certain while, the ball will be out here. Okay. So ball is rolling, no? Ball is rolling. Okay. So it's a combination of rotational motion, omega. It's a combination of omega plus the rolling motion and sliding motion. Fair and fine. Now, instantaneous axis of rotation, most of your teachers are giving you the definition that instantaneous axis of rotation is nothing but the point of contact. It's not that. Instantaneous axis of rotation is that point where the velocity is equals to 0. Huh? Sir, what do you mean by that? Instantaneous axis of rotation is the point in this circle or disc or sphere or ring or whichever circular object it is. Okay? A point in this object, the axis is passing through that point, and the velocity of that point at that instant is equals to 0. So again, what do you mean by that? See, so this rolling motion, okay, I'm divided into rotating motion or rotational motion plus linear motion. Okay. Now check this rotational motion. Okay. This is rotational motion plus linear motion. Okay. Now check this rotational motion. In this rotational motion, suppose a body is at omega, rotating with angular velocity omega. What is the velocity at this point on the surface? It is nothing but omega into r in downward direction. If the radius of the disc or sphere or whichever rolling object it is, okay, if the radius of the disc is nothing means r, the velocity at this point will be omega r in downward direction, isn't it? Velocity is equals to omega r. Okay, what is the velocity at this point? The velocity at this point is nothing but omega r. Okay, the velocity at this point in the disk due to the angular velocity omega is nothing but omega r. Similarly, the velocity at this point would be nothing but omega r. The velocity at this point would be nothing but omega r. Similarly, at any point inside the disk, velocity at that point would be omega into distance from the center. Understood? Omega into this much distance. So the velocity at every point in this disk or sphere or whatever it is nothing but omega into distance from the center. The velocity at this point at the edge of the disk is nothing but omega into distance from the center. Velocity is nothing but this point or omega into distance from the center. Okay, and velocity would be in the direction where the thing is rolling. This much is understood. So velocity at every point is given by omega r. So not velocity at every point. Velocity at surface is given by omega r. Velocity at any point is given by omega into distance of that point from the center. Isn't it? Understood this much? Okay. Now check properly. Due to rotation, this omega r was coming, no? Now, suppose I'm taking translation also, linear translation. Now, suppose a body is moving with velocity v. Okay. This v is independent of the parameters out here. This is very independent. That means this can be anything. It has nothing to do with these parameters. Okay. Understood? Now, for a linear motion means the disk is there. It is going in straight direction. It is not rotating or not rolling or any kind of thing. If the disk is out here, it is going straight with linear velocity v. Okay. What is the velocity at this point? The velocity at this point is also v in this direction. The velocity at this point is also v in this direction. The velocity at this point also is v in this direction. So the velocity of any point in this disk or sphere would be v in the direction of velocity or in the direction of center of mass. Okay. Now, what did I say? Rolling motion is a combination of this motion and this motion. Okay. So while the body is rolling, okay, if I ask, while this body is rolling, what is the velocity at topmost point? The velocity at topmost point is nothing but this velocity plus this velocity. What is the velocity at the surface or this surface? Okay, at this side surface. Velocity at the side surface is nothing but vector summation of this velocity plus vector summation of this velocity or velocity at the surface, isn't it? Omega down plus v in rightward direction. What is the velocity at the bottom? Okay, bottommost point. The velocity at bottommost point is nothing but vector summation of omega r and v. Okay, so velocity at any point in this disk, okay, or sphere, velocity at any point in this disk or sphere is a combination due to rolling motion or velocity out here. Velocity out here is nothing but omega into distance from the center plus the linear velocity of center of mass. Understood? The velocity of any point in a rolling motion is a combination of rotational velocity plus linear velocity. The velocity at this point would be omega r in downward direction, not omega r, omega into this much distance in downward direction plus v in right direction. So the total velocity in rolling motion at any point of the object is nothing but a combination of this velocity and this velocity. Okay. Now the definition of instantaneous axis of rotation. Instantaneous axis of rotation is the axis that passes through the point where the velocity is equals to 0. Okay, instantaneous axis of rotation is the axis passing through the point passing through the point where the velocity, the net velocity, net velocity means velocity due to this rotating motion plus velocity due to this translation motion. The net velocity, this velocity plus this velocity is equals to net velocity. So instantaneous axis of rotation is the axis passing through the point where net velocity is equals to 0. Okay, this is the definition of instantaneous axis of rotation. Okay, understood this much. Now for pure rolling, okay, when the body is rolling without any slipping, that means the body is rolling like this. Okay, there is no slipping at the surface at the point of contact. There is no slipping with the surface at the point of contact. That means there is no motion of drag. For the concept of pure rolling, the necessary condition is V is equals to omega R. Understood? For the concept of pure rolling, the necessary condition is the linear velocity is equals to omega into R. Understood this much? This is the necessary condition for pure rolling. Okay, and for sliding or impure rolling, okay, sliding plus rolling, V is not equals to omega R. Okay, for pure rolling, V is equals to omega R. For impure rolling, V is not equals to omega R. Okay, rolling motion is a combination of rotational motion plus linear motion. Okay, instantaneous axis of rotation is a point where the net velocity, that means velocity due to rolling motion plus velocity due to linear motion is equals to 0. Now for pure rolling, this is the condition. V is equals to omega R. Now for pure rolling, check this point at the point of contact. Okay, for pure rolling, the point of contact is nothing but the contact at which the surface touches the sphere, isn't it? What is the velocity at point of contact? See, omega R in this direction minus V in this direction. And we already know that the magnitude of V is equals to omega R. So omega R and V cancels out each other, isn't it? For pure rolling at the point of contact, omega R and V cancels out each other. Why? Because the condition for pure rolling is V is equals to omega. Okay. So by that condition, the instantaneous axis of rotation becomes the point of contact. Understood? Instantaneous axis of rotation is point of contact. Rotation is point of contact. Understood this much? This is the only thing that you need to know. Okay. There is one more concept that I need you to understand in rolling motion only. This is the first concept that you must very carefully understand. Okay. The second concept of rolling motion. Suppose in a case of pure rolling, let me just do it with a case of pure rolling. Okay. If I do it in a case of pure rolling, you'll understand what is happening. Okay. You can extrapolate it that for impure rolling also. For pure rolling. Pure rolling. Okay. Some of you or most of you have certain doubt. Okay. This wheel is moving. Okay. So I am rotating it like this, omega. Okay. My angular velocity is omega. Suppose I am to take the moment of inertia at the instantaneous axis of rotation. That means I am to take the moment of inertia out here. Okay. If I take the moment of inertia out here, okay, the moment of inertia will pass to this point, isn't it? Okay. In my first case, the moment of inertia, in this case, the moment of inertia is passing through the center of the sphere or center of mass. In the second case, my moment of inertia is passing through the instantaneous axis of rotation. Okay. Sir, what is the angular velocity out here? In some books, they directly give you omega like this. Angular velocity is equals to omega. And you get very confused, sir. If the angular velocity is omega out here with respect to center, how is the angular velocity omega out here also with respect to center? Okay, how does this make sense? Okay, see, if you have no doubt out here and if you have memorized it as it is, good for you. Okay, but if you have doubt out here, that means, sir, how does this equals to this? Okay, you need to understand that I have said little lectures before. Okay, while I was doing Newton's law of motion, if a body, remember that, suppose this is a disc that is rotating with angular velocity omega. Okay, I'm looking this disc from the top. This is a horizontal disc rotating with angular velocity omega, isn't it? I'm looking at this disk from the top. Okay, what did I say? Every point rotates with angular velocity omega with respect to other point inside the disk. That means any 2 points inside the disk. Suppose this disk that was rotating with angular velocity omega. If I take this point and this point, any 2 points, any 2 points inside the disk, okay, any 2 points will rotate with angular velocity omega in the same direction. So how is it? Just check it for yourself. No? Okay, I'll just do a simple check. Okay, suppose I'm taking this point. Okay, I'm checking this point. Okay, now what is the velocity out here? Okay, what is the velocity out here? Suppose I'm observing from, let's say, out here. Okay, or from any inertial frame. Okay, what is the velocity? Suppose my observer is out. Okay, what is the velocity of this point? Omega, isn't it? Velocity of this point is nothing but omega in downward direction. Now, if I put my observer out here, okay, my observer is situated at the edge of the disk. What is the angular velocity of this point? What is the angular velocity of the center? The angular velocity of the center is nothing but in this direction, omega r, not omega r, angular velocity is nothing but omega, isn't it? The linear velocity would be omega r in opposite direction, the angular velocity would be omega, isn't it? So this point or the center is rotating with angular velocity to a observer situated at the edge of the disk, isn't it? Understood? So any point, so if a object or if a disk is rotating with angular velocity omega, any point rotates with angular velocity omega with respect to other point inside the disk. That means this point rotates with angular velocity omega with respect to this point. Even this point rotates with angular velocity omega with respect to this point. Understood? Okay. If you want to observe more carefully, what is the velocity? Okay, what is the velocity at this point? The velocity at this point is nothing but omega, isn't it? Velocity at the surface is nothing but omega in this direction. Okay. Now, if I put my observer out here, okay, if I put my observer out here, what is the velocity at this point? See, there would be an initial velocity, the velocity of the point itself due to omega, and the pseudo velocity. That means this point itself is moving down with velocity, you know. So a pseudo velocity would get added out here, isn't it? Frame of reference. We didn't understand this one. Okay. My question out here was, what is the velocity at this point when I see from ground or when I see from top? Okay, the velocity at this point is nothing but omega. Now, if I keep my observer at this point, what is the velocity of this point as seen by this observer? The velocity of this point as seen by this observer is nothing but the velocity of the observer must be subtracted out here, isn't it? So velocity of the observer is subtracted and the original velocity of the point, isn't it? The original velocity of the point is also there. Okay, so the total velocity of this point as seen by this observer would be nothing but 2 omega r, which is equals to 2 omega r, isn't it? Understood? So the velocity at this point as seen by this observer, okay, would be 2 omega r. Understood this much? Okay, this can also be written as omega into 2r, omega into 2r. So if the linear velocity is omega into 2r, okay, the linear velocity out here is omega into 2r with respect to this point, and the distance between this is nothing but 2r. What is the angular velocity of this point with respect to the observer? The angular velocity of this point is also omega. Understood? So if any object is moving or rotating with angular velocity omega, any 2 points, okay, inside the disk rotates with angular velocity omega with respect to each other. Understood this one? Out here, you need to maintain a caution that the observer out here, okay, is moving with the disk but not rotating with the disk. That means the observer out here, okay, the observer out here is not bolted to the disk. The observer out here is free to rotate. See, one kind of rotation is how to explain? Okay, that won't be important right now. That would be important for you, this parameters of thing. But okay, leave that for now. Okay, just remember, just make a note that the observer is moving with the disk, okay, but not rotating with the disk. That means when this observer comes out here, the eyes of the observer will be in this direction only. The eyes won't be pointed upward. when this observer goes out here, the eyes of the observer will be pointed in this direction only. It won't move in this direction. That means the observer at various point would be somewhat like this. Okay, so if the observer started out here, okay, and is rotating with angular velocity omega, the eyes of the observer would be in this direction only. The eyes of the observer would be in this direction only. The eyes of the observer is in this direction only. That means the observer is moving with the disc but not rotating with the disc. If the observer was moving with the disc and rotating with the disc, what would happen? If the observer was moving and rotating with the disc, what would happen is when he was out here, the eyes would be in this direction. When he came down, the eyes would be in this direction. When he came out here, the eyes would be in this direction. When he came at the top, the eyes would be in this direction. So in our case, or the case that you are understanding, we need to remember that the observer does not rotate with the rotating object. It only moves with the rotating object. Okay, this is the scenario. Understood? Okay, otherwise you need to add some more, pseudo forces called Coriolis forces. So we won't get into this scenario. Okay, the main concept that I gave you out here was when a body rotates. Okay, suppose a body is rolling out with angular velocity omega with respect to center. As soon as I shift my frame of reference to the instantaneous axis of rotation, the whole body would move with angular velocity omega. Not the whole body would rotate with angular velocity omega with respect to the instantaneous axis of rotation. If I shift my instantaneous axis of rotation out here, the whole body would rotate. Understood? The only difference out here is when I'm seeing this from inertial frame. When I'm seeing this from inertial frame means ground frame. Okay, when I'm seeing this object from ground frame, for pure rolling, it will have an angular velocity omega plus linear velocity v. Okay, but as soon as I shift my frame of reference to out here, okay, as soon as I shift my frame of reference to instantaneous axis of rotation, the linear velocity, that means the v component, gets cancelled out. Understood? As soon as frame of reference is moved to instantaneous axis of rotation, the linear velocity is nullified or cancelled out. NULLIFIED. Why is the instantaneous axis of, or why is the linear velocity nullified? Because the frame itself is moving with, see, this out here. Okay, out here. Okay, when I shift my frame of reference out here, I do not have to take any linear means. I do not have to take any linear velocity out here. No. Okay, what's the velocity at this point, or what's the velocity at center? Velocity at center was nothing but omega r, isn't it? Velocity at topmost point is nothing but omega into 2r. Okay, for pure rolling, what is the velocity at this much point, or what is the velocity at point of contact? The velocity at point of contact is equals to 0. The velocity of point of contact is equals to 0. How is it 0? Omega r minus v. Okay, what is the velocity at center? The velocity at center is equals to omega r. The velocity at center is equals to omega r. Why? Because for pure rolling, v is equals to omega r. Okay, what is the velocity at topmost point? The velocity of topmost point is equals to 2 omega r, or omega into 2r. The velocity at topmost point out here is nothing but omega r plus v, where v is nothing but omega. So omega r plus omega r is equals to 2 omega r. What is the velocity at side point? Okay, it's nothing but omega into this much distance in this direction. Okay, if you add in this method, that means omega r plus this v, it will also give a velocity in this direction. Understood? So this omega, or when you're analyzing the thing from center frame of reference, okay, or frame of reference at the center, okay, from ground frame, sorry, when you're analyzing the thing from ground frame, okay, and if you're taking moment of inertia about the center of mass, okay, then you have to consider for rotational thing plus linear thing. Okay, but as soon as you shift your moment of inertia to the point of contact, okay, you do not have to take the linear motion, or you do not have to take the linear parameter. Understood? Okay, if you take your point, or if you take your observer out here and the axis of rotation is passing out here, the moment of inertia of the entire thing would be through this point and calculate for omega only. The main point out here is if it is rotating with angular velocity omega out here, this will also rotate with angular velocity omega to this point. And if you take your point instantaneous axis of rotation at this point, the whole body would move with angular velocity omega with respect to that point. So what I'm saying is, as soon as you shift your frame of reference, doesn't matter which point you take. If you take this point, this would be angular velocity omega. If you take this point, okay, in which motion is it rotating? Rotating in this motion. Okay. Okay. If you take this motion, I think Let me check. Okay, omega. Acha. This should supposed to make a circular path. Okay, they should rotate in the same direction of motion. That means if I put my right hand, same direction of motion. Same direction of motion. Just use your right hand. Okay, same direction of motion. Doesn't matter where you take your observer, it will move with angular velocity omega. Okay, this is the motion that I'm going to, that you must understand. The first notion is concept of pure rolling. The second notion is concept of angular velocity omega. That means if you're taking from down frame, it is omega r plus v. If you're taking from, or if you're taking your calculation from instantaneous axis of rotation, it is only omega. Okay, there is no translational velocity. Understood this one? But that is the only thing that you must understand in rolling. Now let us apply these two concepts. This concept and this concept in numericals. Okay. Now let's solve this question with the principles that you have learned. So in this question, there is a uniform speed that is rolling down a wheel. Okay. Let the angle of the incline be theta. There is a sphere out here. Okay. And is rolling down. Fair and fine. Okay. And the case is pure rolling. Pure rolling, how do I know? Find out the magnitude of friction of coefficient for which slipping is absent. So if slipping is absent, if there is no slipping out here, that means pure rolling. Okay, pure rolling. That means no slipping is occurring out here. Pure rolling means v is equals to omega r, or velocity of the center is equals to angular velocity into radius. Okay. Achha, one more thing. Okay, regarding this rolling motion that I have skipped to tell you, that is, see, in case of pure rolling or impure rolling, that means sliding plus rolling, in both the cases friction force will be present. Without friction force, rolling is not possible. Okay, so in both cases, in case of pure rolling also, in case of impure rolling also, friction force is present. Okay, however, in case of pure rolling, friction force is much lesser than, means mu into n. Okay, friction force is much lesser than kinetic friction, or limit of kinetic friction. Okay, what is the value of friction force? You have to find out using equation. Okay, however, when sliding plus rolling occurs, a situation is there, friction force is equals to mu into n, or friction force is equals to coefficient of friction into normal reaction force. So in both the cases, in case of pure rolling also, friction force exists, which is much lesser than mu into n. In case of impure rolling, friction force is equals to mu n. That means whenever sliding is occurring, friction force is equals to mu into n. Whenever pure rolling is there, friction force is much lesser than mu into n. What is the value of F? I don't know. We have to find out using equation. Understood this much? So out here in the question that you are solving, okay, a body rolls down, or a sphere, uniform sphere, okay, rolls down an inclined plane. The mass of the uniform sphere is m. Okay, we have to find out the magnitude of friction coefficient at which slipping is absent. Okay, and the kinetic energy of the sphere at t second at the beginning. Now my first intuition is you have two options. Sir, how to solve this equation? You can either solve this equation, okay, from this ground frame of reference. You can either solve the problem from ground frame of reference, or you can solve the problem from instantaneous axis of rotation. Both the answers will be equally correct. Okay, so whichever you have to do it. I'll show you, I'll show you both the ways. Let me start with instantaneous axis of rotation. Or I'll solve this problem by using frame of reference, or my frame will be at the instantaneous axis of rotation. That means out here. Okay, fair and fine. So if my frame is out here, the first thing, let me draw the forces mg sine theta. Okay, out here, or out here, mg sine theta. This out here is mg cos theta. Friction force will act in this direction, friction force. The friction force is acting in this direction. Normal reaction force will act in this direction. Normal reaction force will act in this direction. Okay, are there any other forces? Don't think so. Okay, okay. So I'm solving this problem with frame of reference. That means my frame of reference is kept at instantaneous axis of rotation. Okay, and for case of pure rolling, okay, for the case of pure rolling, what is the velocity at instantaneous axis of rotation? 0. Okay, so velocity at this point would be equals to 0, because omega r and v would cancel out each other. Okay, omega r would be in this direction, v would be in this direction. Suppose it is rotating with angular velocity omega, so omega r would be in this direction, velocity would be in this direction, and both would cancel out each other. Fine. Now due to this omega, okay, see, if I see my point out here, okay, there is a torque. If I take my observer out here, there is a torque acting on this sphere. Okay, what is the torque acting on this sphere? The torque acting on this sphere is due to mg sin theta. See, the torque due to friction force would be 0 because the axis is passing through this point only, isn't it? So r cross f due to this friction force is equals to 0. Torque due to mg cos theta is equals to 0. Torque due to normal reaction force is also equals to 0 because all these points f, mg, cos theta and n passes through the axis of rotation or instantaneous axis of rotation. Okay, so my only torque would be due to mg sin theta. So torque is equals to I into alpha, or alpha is the angular acceleration. Alpha is the angular acceleration. Okay, alpha is the angular acceleration. Okay, so if the body is rotating with angular acceleration alpha, okay, from the center of mass, if I shift my frame of reference out here, this whole body would rotate with angular acceleration alpha like this, isn't it? It doesn't matter. I've explained this before. Okay, if from ground frame of reference the angular acceleration is alpha, if I shift my frame of reference at the instantaneous axis of rotation, my angular acceleration will also be alpha. The only difference out here would be from ground frame of reference there would also be a linear acceleration in this direction. Okay, but a is equals to alpha into r in case of pure rolling. However, at instantaneous axis of rotation there would be no linear acceleration, or the linear component of acceleration would be absent. Understood? Okay, this much is understood. For pure rolling, v is equals to omega r. Okay, where is that? For pure rolling, v is equals to omega r, a is equals to alpha r, a is equals to alpha r, and displacement s is equals to theta into r. Okay, so in case of pure rolling, these are the three conditions. Okay, okay, so my point of reference is out here. The torque is due to mg sin theta only. So torque is nothing but mg sin theta into r. Why? R cross mg sin theta. This is the force. Torque due to this force at this point of rotation is nothing but r into mg sin theta. Moment of inertia. Moment of inertia of the whole sphere about this point, or about instantaneous axis of rotation, is nothing but moment of inertia through the center, a solid uniform sphere. Okay, uniform sphere, moment of inertia of a uniform sphere is nothing but 2 by 3 m r square. But this moment of inertia is through the center, isn't it? I have to find out the moment of inertia through the instantaneous axis of rotation. So if I apply parallel axis theorem, it would be plus m r square. So the moment of inertia of the whole sphere through the instantaneous axis of rotation is nothing but this value is equals to alpha, or angular acceleration alpha. Okay, now the question is mostly solved. If I do this one, or mg sin theta into r is equals to 2 by 3 m r square plus m r square is nothing but 3, 6, 3, 4, 5. So if I take LCM out here, it would be 3, okay, 3, 5, 5 by 3 m r square. It would be 5 by 3 m r square. Acha, one more thing, I've done a little bit wrong. Okay, the moment of inertia of a uniform sphere is not 2 by 3 m r square, it is 2 by 5 m r square. Little bit wrong out here, 2 by 5 m r square. Okay, it's not 2 by 3, sorry, 2 by 5. This is my mistake. I made a formula error. Okay, the moment of inertia of a spherical shell is 2 by 3 m r square. 2 by 3 m r square. For whole sphere or uniform sphere or a solid sphere, there is nothing but 2 by 5 m r square. Okay, so the moment of inertia through this point would be 2 by 5 m r square plus m r square. This is nothing but 7 by 5 m r square, isn't it? Into alpha. So m and m would get cancelled, r and r would get cancelled, or I would have g sin theta is equals to 7 by 5 r into alpha. Then fine. Now the magnitude of friction coefficient for which slipping is absent. Okay, so I haven't taken any parameter of alpha. Okay, so now for pure rolling, okay, we know that alpha is equals to, sorry, a is equals to alpha r. For pure rolling, a is equals to alpha into r. So a is equals to alpha into r, or alpha is equals to a by r. So pure rolling, alpha is equals to a by r. So g sin theta is equals to 7 by 5 r into a by r. Okay, so g sin theta is equals to 7 by 5 a, or a is equals to 5 by 7 g into sin theta. So the linear acceleration that would occur out here, or the linear acceleration of this block as observed from ground frame of reference, is nothing but 5 by 7 g sin theta is equals to 5 by 7 g sin theta. I'm just playing with equation. Okay, the condition for pure rolling is nothing but v is equals to omega r, a is equals to alpha r, and s is equals to theta r. Okay, using that condition I have obtained this equation. Okay, now the magnitude of friction force for which slipping is absent. Now let me shift my frame of reference to ground frame of reference. Okay, and let me solve this problem with linear mechanics. Linear mechanics means there are two forces, mg sin theta and friction force, mg sin theta and friction force, and due to these two forces there is an acceleration. Okay, so mg sin theta minus friction force is equals to mass into this acceleration. So mg sine theta minus friction force is equals to mass into acceleration. The value of this acceleration is nothing but how much? 5 by 7 g sine theta. 5 by 7 g sine theta. This 5 by 7 g sine theta is nothing but the linear acceleration. Okay, from ground frame of reference. Rolling motion is nothing but a combination of rotational motion plus linear motion. Okay. Now the magnitude of friction coefficient for which slipping is absent. That means the value of friction force is at the limiting value. That means just I have to adjust this friction force. That means if I have the ability to adjust the coefficient of friction, I have to adjust the coefficient of friction in such a value that if I increase it by 0.0001 amount or little bit amount also, what will happen? It would start rolling. Okay, that means if I decrease it by little bit amount also, it would start slipping. Okay, if I have to adjust this value at such an amount that if I decrease by little bit also, little bit means 0.00001, very less, this block would go from pure rolling to slipping plus rolling. Okay, that means my limiting value out here is nothing but mu into n. That means just before or just after slipping, okay, I've increased the coefficient of friction such that this value, or if I increase it a little bit more also, it will start means pure rolling. It is also already in pure rolling motion. That means if I just decrease the value of coefficient of friction, okay, it will start slipping. Understood? So my limiting value out here is nothing but mu into n. Fair and fine. I have to find out the value of mu, or limiting value of mu. Okay, if the limiting value of mu means if the value of mu, actual value of mu, is much lesser than anything that I obtain out here, the ball or the sphere would start slipping or sliding. Okay, it would not be pure rolling. And if the value of coefficient of friction out here, okay, is anything that is greater than the value that I found out here, this ball or this sphere would keep on pure rolling. Understood? So this is the limiting value after which pure rolling starts. Okay, what is the value of n? N is nothing but the normal reaction force. Normal reaction force is nothing but mg cos theta. Okay, normal reaction force is nothing but mg cos theta. So if I solve this equation, is nothing but mg sin theta minus mu mg cos theta is equals to 5 by 7 mg sin theta. So if I just solve this problem, mg sin theta minus mu mg cos theta is equals to how much? How much is it? Mg sin theta minus mu mg cos theta is equals to 5 by 7 mg sin theta is equals to 5 by 7 mg sin theta. Now let's solve this problem. Okay, mg, g and g. M and g will get cancelled. So sin theta minus mu cos theta is equals to 5 by 7 sin theta. Okay, let's group together sin theta. So sin theta minus 5 by 7 sin theta is equals to mu cos theta. I just send this to the left hand side and this mu cos theta to the right hand side. So if I take sin theta common, 1 minus 5 by 7. 1 minus 5 by 7 is nothing but 2 by 7. Yeah, 2 by 7 is equals to mu cos theta. Or sin theta 1 minus 5 by 7 is nothing but 2 by 7 is equals to mu cos theta. Or sin theta by cos theta. That means if I take this cos theta down out here, sin theta by cos theta is nothing but tan theta is equals to 2 by 7. I'm taking this 2 by 7 to the right hand side. This is nothing but 7 by 2 mu. So this is my answer. So the coefficient of friction mu is nothing but 2 by 7 tan theta. Okay, 2 by 7 tan theta. At this coefficient of friction, that means if this surface has friction coefficient higher than this value, okay, if this actual surface has a friction coefficient higher than this value, then it would keep on rolling. If the actual coefficient of friction out here is lower than this value, that means it would start sliding. Okay, understood the concept? Now the second part of the question, the kinetic energy of the sphere t second after the beginning of motion. Okay, so for kinetic energy, see, since I'm considering by this frame of reference or frame of reference on the instantaneous axis of rotation, kinetic energy is equals to half I omega square. Kinetic energy is equals to half I omega square. Okay, is there any translational motion when I'm doing from this frame of reference or from the frame of reference from instantaneous axis of rotation? Is there any translational motion? No. So there is no translational kinetic energy out here. Okay, so when I'm viewing or when I'm writing the kinetic energy from instantaneous axis of rotation, there is no translational kinetic energy. Okay, so half I. What is the value of moment of inertia? Moment of inertia is nothing but 7 by 5 mr square. I've already obtained, no? 2 by 5 mr square plus mr square is nothing but 7 by 5 mr square. 7 by 5 m r square. Now my question is, what is the value of omega, or what is the value of angular velocity at certain time t? See, if this keeps on rotating with angular acceleration alpha, okay, what was the initial angular velocity? The initial angular velocity was 0. The uniform starts of mass m and radius r rolls without slipping at an inclined plane. Okay, t seconds after the beginning of motion. Beginning of motion means initial angular velocity and initial linear velocity or initial velocity is equals to 0. So at the beginning of motion, angular velocity is equals to 0. After t seconds, what would be the angular velocity? If I have the angular acceleration alpha, my question is, after t seconds, what would be the angular velocity? Can I write v is equals to u plus at, s is equals to ut plus half at square, v square is equals to u square plus 2s, and write those, no? So if I write v is equals to u plus omega t, or omega final is equals to omega initial plus alpha into t. Okay, what is omega initial? 0. Why? Because from the beginning of motion, that means initial angular velocity is equals to 0. Alpha is given. So omega final is equals to, what is the value of alpha? The value of alpha, what is the value of alpha? What is the value of alpha? Alpha is equals to 5 by 7 g sin theta by r. Okay, so the value of alpha out here is nothing but 5 by 7 g sin theta into divided by r. Okay, so value of alpha is equals to 5 by 7 g sin theta divided by r into t, isn't it? Okay, so omega final at time t is equals to 5 by 7 g sin theta divided by r into t. So you just have to substitute this omega final out here. That is the angular velocity at time t, no? And that is what is being asked in the question. The kinetic energy of the sphere at time t after the beginning of motion, isn't it? So at time t, okay, angular velocity is nothing but 5 by 7 g sin theta by r into t whole square, omega square, whole square. And if we solve this one, we'll get the kinetic energy. So this is part B of the problem. Okay, part A of the problem, this one. Part B of the problem is this one. Now you might say, sir, very good, but I have to do the same problem from the ground frame of reference. Okay, I have to solve the same problem from ground frame of reference. That means I do not want to use the instantaneous axis of rotation. I'll say fair and fine. Okay, let's do it from ground frame of reference. So from ground frame of reference, let's see. Okay, what it is. Okay, from ground frame of reference, let me just okay, from ground frame of reference. Okay, my axis of rotation would pass through the center of sphere, isn't it? And rolling motion is nothing but sliding motion plus rotational motion. And for pure rolling, V is equals to omega r, A is equals to alpha r, and AC is equals to theta r. This much is certain. Okay, so let me use my equation, or let me write out my equation from ground frame of reference. So they will form two equations. First one is torque equation. Okay, torque equation means from ground frame of reference. If I keep my axis at the center, okay, if I keep my axis at the center, only one force is causing the torque, and that is nothing but the friction force, isn't it? Mg cos theta passes through the axis of rotation, N also passes through the axis of rotation, Mg sin theta also passes through the axis of rotation. So the only force that causes the torque is nothing but friction force, isn't it? So let me write down this one, or let me just copy this one. Okay, otherwise you won't understand if I don't copy the diagram. Let me just copy the diagram. So the diagram has to be copied. Okay, okay, let me paste it out here. Okay, I'm writing my equation from ground frame of reference. So from ground frame of reference, okay, what is causing the torque? This friction force. So torque is equals to I alpha. Torque is nothing but F into R, isn't it? That means while I'm observing from ground frame of reference, my axis of rotation is at the center. Okay, fair and fine. F into R is nothing but torque. Moment of inertia. Out here, moment of inertia would be from the center, or from the center axis of rotation. That means the moment of inertia out here would be only 2 by 5 m square. We do not have to shift the moment of inertia out here. Okay, into alpha. This is my equation 1. However, when I'm observing from ground frame of reference, I have to add another equation. What is that another equation? Mg sin theta minus friction force is equals to mass into acceleration. Why? Because this ball is translating also, no? It is moving in a straight line also, no? It is accelerating in this line also, no? So this is my torque equation. The second one would be my force equation. And my force equation says that mg sin theta minus friction force is equals to mass into acceleration. And for pure rolling, acceleration or A is equals to alpha into r, isn't it? For pure rolling, A is equals to alpha into r. Okay, so from this problem we get, or from the first equation we get, if r is equals to 2 by 5 m r square, 2 by 5 m r square into alpha, or r and r would get cut. Okay, or F would be equals to 2 by 5 m r alpha. If I substitute the value of F, 2 by 5 mr alpha, I'll get the value of mu. Mg sine theta minus 2 by 5 mr alpha is equals to m alpha r. Okay, so I'll group together these two, or mg sine theta is equals to m alpha r plus 2 by 5 mr alpha. Mr alpha can be also written as m alpha r. So m alpha r plus 2 by 5 m alpha r. This is nothing but 7 by 7 by 5 m alpha r. So mg sine theta is equals to 7 by 5 m alpha r. Okay, m and m will get cancelled. Okay, so angular acceleration g sine theta is equals to 7 by 5 into alpha is nothing but a by r in case of pure rolling into r, or 5 by 7 g sine theta is equals to a, or linear acceleration is equals to 5 by 7 g sine theta. See, it is the same thing that I obtained out here, 5 by 7 g sine theta. Okay, and the remaining process is the same. You obtain the linear acceleration, then you apply the limiting value. That means you apply linear mechanics at limiting value. This will just start to slide, isn't it? So it doesn't matter if you use instantaneous axis of rotation or ground frame of reference. Both the answer will be correct. You just need to remember the points that I gave you. Okay. After this, apply linear motion, linear equation. Mg sin theta minus limiting value is equals to m mass into acceleration. Okay. In case of pure rolling, a is equals to alpha r, and apply this one. You'll get the value of mu. Okay. Then after getting the value of mu, substitute the value of mu in alpha. Okay. Now for kinetic energy. Okay. Kinetic energy, you have to use I is equals to 2 by 5 mr square. But the answer won't become same, no? The value of omega out here would come as same. Everything would come as same. But if you use the value of I is equals to 2 by 5 mr square. See, from ground frame of reference. From ground frame of reference, my axis of rotation is at the center. The moment of inertia through the center is nothing but 2 by 5 mr square. So if I use 2 by 5 mr square, if I use 2 by 5 mr square out here, the answer is supposed to change, you know. So what is happening out here? See one thing and pay attention very carefully. When you are applying from ground frame of reference, there is a rotational kinetic energy. That means you have to apply this one. You have to apply this one, 2 by 5 mr square into angular velocity whole square. Then fine. You also have to add translational kinetic energy. From ground frame of reference, this is rolling plus sliding, no, plus moving, isn't it? From instantaneous axis of rotation, this is rolling only. Okay, so there is no translational motion. But while you are observing from ground frame of reference, this is rolling, so there will be rolling kinetic energy plus translation kinetic energy. Okay, so in case of kinetic energy, see, the in between processes are from acceleration you have to find out the coefficient of friction, the same process. From coefficient of friction you have to find out the angular velocity, same process. Now for kinetic energy is equals to rotational kinetic energy plus translational kinetic energy, isn't it? Rotational kinetic energy plus translational kinetic energy. When you are applying the kinetic energy from instantaneous axis of rotation, you simply apply 7 by 5 mr square. There is no translational component of kinetic energy. But as soon as you shift your frame of reference to rotational kinetic energy, as soon as you shift your frame to ground frame of reference, the rotational kinetic energy becomes half I. I is nothing but 2 by 5 mr square. 2 by 5 mr square into omega. The value of omega will come same as this one. 5 by 7 g sine theta r into t. 5 by 7 g sine theta by r into t. By r into t whole square. Okay. Plus half mv square. Half mv square. What is the value of v? What is the value of velocity? The value of velocity is nothing but v is equals to u plus at, isn't it? Initial velocity, or if I write this in angular velocity terms, omega r is nothing but omega final into r is equals to omega initial into r into plus alpha r into t. Okay, so I have to find out the value of v square. V square means nothing but omega final into r whole square. So if I find omega final, this parameter, this entire parameter, this parameter will become 0 because initial angular velocity is equals to 0. Omega final into r is equals to alpha. The value of alpha, what is the value of alpha? The value of alpha. The value of alpha is same in both cases. The value of alpha is nothing but, what is the value of alpha? 5 by 7 g sine theta by r. The value of alpha is nothing but 5 by 7 g sine theta by r. Where did I find out? 5 by 7 g sine theta by r. Okay, this is the value of alpha. into r. Into r is nothing but this r. Okay, into t. Now, if I cancel out the r and r, omega final into r is equals to 5 by 7 g sine theta into t. And omega final into r is nothing but linear velocity. In case of pure rolling, v is equals to omega final into r. So out here it is nothing but omega final into r. So if we substitute this value in case of this and add these two together, we'll get the same answer as this one. Okay, see, all the parameters will be same. Out here only just add and look it up. Okay, the same thing will happen. Now, in this setup, we need to find out the tension in these two plates and the angular acceleration of this block. Okay, so let me draw the same diagram from this side. That means I'm seeing this diagram from this side. Okay, so I'll see something like this. Okay, this is a log, and this log will fall down. Tension out here is T. Very fine. And due to symmetry, the tension on this rope will be equal to tension on this rope. Due to symmetry, tension on this rope is equal to tension on this rope. What do I mean by symmetry? Symmetry means this much distance or distance of this rope from the edge is equal to distance from this rope from the edge. See, these parameters are not given in the question, but somehow you have to go through these assumptions. Why? Because the number of equations, okay, see, there are not sufficient number of information available to take this tension and take this tension different. Okay, so to assume that both the tensions are same, and if both the tensions are same, that means the diagram is symmetrical. That means this much space is equal to this much space. Fine. Now, where do you want to write your equation from? From the instantaneous axis of rotation or from the ground frame of reference? Let's say from the C. I have already done this kind of problem from ground frame of reference. You have to take means the first equation is rotational equation, the second equation is linear equation. Torque is equals to I alpha, force is equals to mass into acceleration, isn't it? And find the relation between both. Out here I'll solve the same problem for instantaneous axis of rotation. So instantaneous axis of rotation is a point or is an axis that is passing through a point where velocity is equal to 0. So at this point, okay, the velocity of this point or the instantaneous velocity of this point would be 0, isn't it? After that only the ball will roll down. No? So this is my instantaneous axis of rotation. And through this point there will be an angular acceleration alpha. Okay. So let me solve the problem. Okay. In this equation or in this problem, let's see. This is my point or this is my axis of rotation, isn't it? This is my axis of rotation. There are two forces, mg force and tension force. Okay. Actually, the tension force would be 2T, tension due to the first T and tension due to the second T. T plus T is equals to 2T. Tension due to both the ropes is equals to 2T. So if I consider my axis out here at the edge, what is the only force that is causing a torque? This mg. So net torque is equals to I alpha, isn't it? Net torque is nothing but m into g into r, where r is the radius of this block. R is nothing but radius of the block. R is radius of the block. Okay. Now, I. What is the moment of inertia of a cylinder? Moment of inertia of a cylinder is nothing but m square by 2. M square by 2. But out here, the moment of inertia, whenever I take moment of inertia as m square by 2, that means I'm assuming the moment of inertia to be taken from the center, isn't it? But is my axis of rotation at the center? No, my axis of rotation is out here. So I have to take the moment of inertia through this point. No, that means my axis is passing through this point, isn't it? So if my axis or moment of inertia through the center is m square by 2, what is the moment of inertia through this axis? I have to apply parallel axis theorem. So moment of inertia through this axis is nothing but m square by 2 plus m square plus m square, isn't it? Into alpha. So I'll get, let me solve the problem. mgr is equals to m square by 2 plus m square is nothing but 3 by 2 m square, 3 by 2 m r square alpha. Now let's cancel the m part, r square part, or g is equals to 3 by 2 r alpha, or alpha is equals to 2g by 3 r. Alpha is equals to 2g by 3 r. This one is understood, isn't it? So the angular acceleration to this one would be 2g by 3r. Okay. So, okay, the tension in is trading. Now, if I find out the angular acceleration, then I need to find out the linear acceleration from ground frame of reference. That means if an observer is observing from ground, what is the linear acceleration of center of mass? Okay. So if this is the point of, what can I say? instantaneous axis of rotation. So if this is instantaneous axis of rotation, okay, that means the velocity at this point is equals to 0 and our frame is out here. Okay, you can imagine this same scenario as a block or as a cylinder rolling downwards, and this is the road. The rope is the road, isn't it? And this point is the instantaneous axis of rotation. So can I say if this angular acceleration is alpha, the angular acceleration through the center, would also be alpha. I have explained this before. That means if any point rotates with angular acceleration, every point inside the disk rotates with angular acceleration with the same angular acceleration with respect to each other. I have explained this point before. That the point is, if this angular acceleration is alpha, this angular acceleration throughout the center or through the center of rotation is also alpha. I have explained this before. Do not get confused about it. Okay. Now my question is, what is the relation between alpha and A? Where A is nothing but the downward linear acceleration. That means if I observe this, or if I observe the same situation, suppose this is the same situation that I'm observing. Okay. If I observe this from ground frame of reference, okay, this is 2t, out here mg. This thing would have an acceleration and this would rotate with angular acceleration alpha, isn't it? Both would be present. From ground frame of reference, angular acceleration would also be present. Linear acceleration of center of mass will also be present, isn't it? However, this angular acceleration is equal to this angular acceleration. I've explained this point before. Do not get confused out here. Okay. Now, from ground frame of reference, if I apply laws of motion or linear equations, linear equation means force is equals to mass into acceleration, or net force is equals to mass into acceleration. So out here, this is A. Okay. This is A. So out here, if I draw out the forces, what are the forces? 2t, mg. Are there any other forces? No. So mg minus 2t is equals to mass into acceleration. Okay. And what is the relation between angular acceleration alpha and linear acceleration A? A is equals to alpha r. A is equals to alpha r. Why? Because see, this is the instantaneous axis of rotation. You can consider the velocity at this point to be 0, isn't it? Now imagine this to be a road, or imagine this string to be a road, or imagine this rope to be a road, and this cylinder is rolling down. Okay. So angular acceleration alpha is nothing but A into r. This is a case of pure rolling, isn't it? Understood? Angular acceleration is equals to alpha into r. This is the point that you need to understand. If you consider, or if you analyze this scenario, okay, as a road, this string or this rope is nothing but a road, and this log or this log is rolling down the road. Okay, and this is the instantaneous point of, or instantaneous axis of rotation. Understood? So if the angular acceleration is alpha, I can simply say A is equals to alpha, no? Because out here pure rolling is occurring, isn't it? There is no slipping out here. Understood this point? So if A is equals to alpha r, I can easily write the value of A out here, because I already got the value of alpha. Okay, so A is equals to alpha into r. So A is equals to alpha into r. What is the value of alpha? 2g by 3r into r, or A is equals to 2g by 3. So mg minus 2t is equals to m into, what is the value of acceleration? 2g by 3. 2g by 3. Okay, so if I solve this question on the next page, or if I solve the equation on the next page, mg minus 2t is equals to 2mg by 3. mg minus 2t is equals to 2mg by 3. So I need to find out the value of tension force. Or 2t is equals to mg minus 2 by 3 mg. Or 2t is equals to mg by 3. mg by 3. Understood this much? So the total tension force. Okay. Let me see out here. So the total tension force applied by both the strings is nothing but 2 mg by 3. Sorry, not 2 mg by 3, it's mg by 3. The tension force applied by this rope plus tension force applied by this rope is equals to mg by 3. This was the first part of the question. Now the second part of the question, the time dependence of instantaneous power developed by the gravitational force. Okay, this is nothing but formula based. Power is nothing but force into velocity. Power is nothing but dot product of force into velocity. Okay, and I need to find out the instantaneous power developed by gravitational force. So what is the gravitational force? Mg. Okay, what is the value of velocity? The velocity at time t would be found out using v is equals to u plus at, isn't it? Where initial velocity is 0. See, starts descending, that means initial velocity is equals to 0. Okay, and acceleration is constant. So by using v is equals to u plus at, where initial acceleration, or sorry, initial velocity is 0. The value of acceleration is nothing but 2g by 3. A is equals to alpha r. This value, A is equals to alpha r. This is nothing but alpha r. I have already said that. Okay, A is equals to alpha r. So the value of acceleration is equals to 2g by 3. The value of acceleration is equals to 2g by 3. So V is equals to 2g by 3 into t. Okay, and if I substitute the value out here, 2g by 3 into t. So the value of power at time t is equals to mg square 2mg square by 3 into t. What I simply did out here is multiply these two. Now some of you might say, sir, isn't this dot product? Yes, obviously dot product. F into V into cos theta, where cos theta is nothing but angle between A vector and V vector. Out here, what is the angle between A vector and V vector? Velocity is also in downward direction. Okay, initial velocity is 0. If acceleration is in downward direction, velocity will also be in downward direction. The job of velocity vector is to follow the acceleration vector, isn't it? So velocity vector will also be downward. Force vector on mg, force vector is also downward. So cos 0 is nothing but 1. So it's simply multiply there, isn't it? So power is equals to mg into 2g by 3 into t. So 2mg square by 3 t. So this is the power. So this is for question number 1.25. You can also solve this problem from ground frame of reference. But while using ground frame of reference, remember that you have to take two equations. One is rotational equation. Okay, torque is equals to I alpha, where I is equals to this m square by 2. Okay, torque about the center, m square by 2 into alpha. And force equation is nothing but 2t minus mg is equals to m into a. Okay, but if you are using this instantaneous axis of rotation, you will not need to take linear accelerations out here. Okay, but you have to take the moment of inertia through this point. Understood? Both are the same thing. Both methods will apply the same answer. On both methods will arrive at the same answer. It doesn't make a difference. Okay.